Bode plots. In theory, you've already learned about Bode plots. In an effort to help you remember what you've learned and be able to use it again this semester, this is a review of how to do straight line approximations of Bode plots. It's divided into 3 parts. I'm going to introduce a general overview of the idea of Bode plots and semi-log paper. I'm going to present to you what you would draw for a straight line approximation for each of the common elements of a Bode plot, and then I'll work out some example problems. You know that the response of a system in the frequency domain is the product of the input and the frequency response. And that frequency response can be divided into a magnitude and a corresponding phase. As to how much of the signal will propagate into the output depends on the content of our H. The type of filter it is depends on the shape of the magnitude and where H is closer to 1 or greater than 1 and where it's closer to 0. The phase also contains information, but we're not going to work with that in this video. We're going to look strictly at how we can represent this magnitude to get an idea about how much of our signal will pass into the output. Our frequency response can have several forms. Usually it's polynomial, particularly if our system is described by a linear constant coefficient differential equation. The numerator may or may not have a zero-order term, and we can have several different orders. It can be a low order or it can be a high order polynomial. And it's a polynomial with respect to the variable j omega. To do the Bode plot, we want to factor it, hopefully, into first order terms. If any of these roots are complex, then we'll have second order terms, and that's okay. So whatever we have, when we do a Bode plot, we're going to be looking at 20 times the log base 10 of that frequency response. And because logarithms take products and convert them into sums, that enables us to take each of these individually, draw them out, and then add each of these components. We're going to do the drawings on semi-log paper, where we have a log scale on the x-axis and a linear scale on the y-axis. Now the y-axis is only somewhat of a linear scale because we're going to plot the y-axis in terms of dB, decibels, and that's a logarithmic factor too. But it's linear with respect to dB. It's logarithmic with respect to omega. It's important that you know how to use semi-log paper. This particular example, I did not label anything because quite often the paper does not come labeled and you need to know how to label it. So I really want you to focus on this. Semi-log paper is broken into decades, groups of 10. Decade comes from the Greek word deca, which means 10. This first line corresponds to 1, the second line to 2, 3, 4, 5, 6, 7, 8, 9, and back to 10, which is a factor of 10 greater than where we started. We then repeat with a 1, 2, 3, 4 until we get to a 10 again. Each of these are 1 decade. It is also 1 decade if we take 3 and multiply by 10, going from this 3 to this 3. If we were to think about omega in a linear space, and then take the log base 10 of it, we get these values here. And notice how that log value has a big step between 1 and 2, smaller between 2 and 3, smaller yet between 3 and 4, and the step keeps getting smaller and smaller between every subsequent pair of numbers. Likewise, between 10 and 100, taking steps of 10, we get the big jump between 10 and 20, a smaller jump between 20 and 30, until we're at a very small jump between 90 and 100. This is our big jump between 1 and 2, slightly smaller between 2 and 3, and very small between 9 and 10. Big jump between 10 and 20, smaller between 20 and 30, very small between 90 and 100. As to which decades we use depends on our application. We could start with 1 and go up to 100. But make sure you think of them in groups of 10, because after 10 does not come 11. After 10 we start over again, and again multiply, and we've got 10, 20, 30. This first decade is in terms of ones. The second decade is in terms of tens. We could have just as easily had the first decade in terms of 1/100th, and the second decade in terms of 1/10ths. Or the first decade in terms of 100ths, and the second decade in terms of 1,000ths. So generally when we look at semi-log paper, we only focus on these starting and ending points of our decades and decide which power of 10 they correspond to, and label that. Okay, now into how do we actually draw Bode plots. One possible form of our h of j omega is just linear in j omega. And when we take the straight line approximation of this, when omega is 1, we have 1 over 1, the magnitude of that is 1, 20 log base 10 of 1 is 0, and we're going through here when omega is 1 at 0 dB. If we have 1 over j omega, so this is an order 1 polynomial, our n is 1, and we will have a slope of our line at minus 20 dB per decade. If we have j omega squared, then n is 2, and we have a slope of negative 40 dB per decade. For every order, we get 20 dB per decade. When we have just the j omega form, we have a straight line and no corner points. And you really need to focus that at omega is 1, we go through 0 dB. If j omega is in the numerator, then we're positive, and we have a positive slope with a slope when n is 1, just j omega, of 20 dB, and when our n is 2, because we have j omega squared, slope of 40 dB. By the way, if we have j omega cubed, what do you think we have? Yep, 60 dB per decade. What does it mean to be 20 dB per decade? We talked about decades, going from 1 to 1 is 1 decade. So in that 1 decade, we want to go up 20 dB. And then we draw a straight line. If we were to go backwards 1 decade, we go down 20 dB. If the form of our element is 1 over 1 plus j omega divided by something, it will not be a straight line. It will be piecewise linear, being flat at 0 dB until we reach whatever value we have below j omega. Call that p for pole. At that value of omega, we then turn and we decline at 20 dB per decade. So this particular p is drawn at 3. 1 decade further forward is at the next 3, and there we're going to go down 20 dB. If we have 1 plus j omega divided by something in the numerator, whatever j omega is divided by, we'll call it z for 0. At that point, we're flat before that at 0 dB, and at that point, we start increasing at 20 dB per decade. Again, 1 decade would be from 3 to 3. If z were at 4, it would be 4 to 4. And then at that point, we go up 20 dB, and we have a straight line. If when we try to factor things, we cannot factor it to get real roots, leave it in quadratic form. Do not have it factored into complex elements. The j that goes with j omega should be the only complex thing you're looking at in your equations. All the coefficients should be real. Make sure you start with a 1 and factor this last term so you get something squared. And whatever that value is, it's called the natural frequency, omega n, n for natural. We're going to be flat at 0 dB before there. At that point, we're going to turn. It's in the denominator, so we'll go down, and because it's second order, we get negative 40 dB per decade. Go forward 1 decade, in this case from 4 to 4, and then go down 40 dB. and draw a straight line between them. If the complex roots come in the numerator, again, do not factor. Rewrite it with a 1 in the front, and make sure you square whatever you have for your coefficient for j omega. Find that natural frequency, squared, and we're in the numerator, so 40 dB plus, go up at 40 dB per decade. Those are the elements. There is one more, constants. Once we start factoring things, there's usually some constants left over. Take 20 log base 10 of that constant and draw a flat line at that value. That will shift things up and down. Okay, let's try some examples. Start really simple. 1 divided by 1 plus j omega divided by 5. We have a first order in the denominator, and our p-value is 5. We need to figure out how to label things. We're looking for 5. We could be here or we could be here. If we put it here, we have more room to show information in our plot. So if we want this to be 5, this should be 1, this should be 10, and this should be 100. Those are the important things to label on your Bode plot. We then need to label our amplitudes. Since we tend to increase 20 dB per decade, this might be a good place to start. Make sure you show a large enough spacing so you can see some detail, but not so large that you run out of paper. We're going to have a flat line at 0 dB until we get to j omega is 5. We're then going to come over 1 decade from 5 to the next 5, go down 20 dB and put a dot, then play connect the dots. We're good to go. This is your answer. This is a straight line approximation for this transfer function. If you were to plot the actual value for this, it would be rounded here at the corner. Some people care about exactly how it is rounded, and they're entitled to that. I'm focusing here on straight line approximations. These are useful to give you a really quick estimate of what things look like, so you can continue a conversation and design things. My opinion is you can get the exact details by then putting it into MATLAB or some other approximation software. But you want to be able to do straight line approximations by hand to use them as a design and analysis tool. Okay, let's try this example. J omega, and it's in the numerator. We said j omegas will always go through omega equals 1 at 0 dB. So our Bode plot has this sort of scale. We want omega equals 1, so let's put that right in the middle. We have a constant out in front of 5. 20 log base 10 of 5 is 13.9. So we can keep approximately the same scale we had before. And there's where 13.9 shows up. Someplace around there. Not exactly, but get approximate. We know our j omega, when omega is 1, will be at 0 dB. Let's go forward 1 decade. And what's in the numerator, go up 20 dB. We could also go backwards 1 decade and down 20 dB. And we play connect the dots. Now we said that with logarithms, what's multiplied will then be added, so we're going to add these two graphs. Coming over here, we have a 13 and a minus 20. That's going to add up to negative 7. So that's going to take our plot and move it up to here by our 13. And that's our final answer. Okay, slightly more complicated. We need to work on rewriting this first. All the rules I gave said 1 plus j omega divided by something. Here we've got a 1, but it's j omega times something. Here we don't have a 1. Here we don't have a 1. We can take this 8 and turn it into a 1 divided by 0.125. We can factor the 6 out of this term, putting the 6 in the denominator. We can factor the 9 out of this term, putting the 9 in the denominator. Now we need to have a Bode plot that shows 0.125, 6, and 9. So this choice of decades will get us there. The constants we have are 5 divided by 6 times 9, 5 divided by 54, which is minus 20.66. So minus 20 minus 21. So again, this sort of scale will do us good for starts. There's our constant term around minus 20. Our 0.125 is here. Our 6 is here. And our 9 is here. For our first term, it's going to be flat till we get to 0.125. 125 is someplace between 0.1 and 0.2. Now we need to go forward 1 decade. Is in the numerator, go up 20 dB. Put another dot, and play connect the dots. For the next one, we're over here at 6. It's flat till we get there. Go forward 1 decade. It's in the denominator, go down 20 dB. Put another dot, play connect the dots. Finally, we have this term with a 9. It's right here. It'll be flat till we get there. Go forward 1 decade. It's in the denominator. Go down 20 dB. Put a dot. Play connect the dots. Okay, we've got all the elements. Now we need to add them. When we start over here from 0 up to here, we've got 0 plus 0 plus 0 plus minus 20, all with a slope of 0. So that adds up to here. Now we have a slope of plus 20 dB per decade. So from this point to this point, we're going to go up 20 dB, and there'll be a line, but we're only going to continue that line until we get to the next corner point. So our answer only continues to there. At this point, we have a slope of plus 20, slope of 0, slope of negative 20, slope of 0. So we're going to have a slope of 0 until the next corner point. From this corner point, plus 20, minus 20, minus 20, 0 gives us a slope of negative 20. Go forward 1 decade, go down 20, put a dot, and play connect the dots. And that's the answer. Okay, one was a second order term. Again, we need an initial constant of 1. So we'll factor the 100 out, which would give us j omega squared divided by 100, and that 100 can be brought inside of the parentheses of the squared as a 10. This term doesn't matter. We're not going to use it for the straight line approximation. It's used for other things, but we don't need it for the straight line approximation. We know we need to be at omega equals 1 and omega equals 10. And we can't do that with 2 decades because we need information before omega equals 1 and after omega equals 10 in order to show what's happening. Therefore, we need 3 decades. And we need information at 1 and information at 10. So this is the set of decades we want to use. Our constants are 5 divided by 100. 20 log base 10 of that is negative 26. So we're going to be down below 20, so we need to make sure we have enough room below 20 to do some plots. Also, we know we're going to be at a slope of negative 40 dB per decade, squared in the denominator. So from 0, we're going to be going downhill quite a bit. So let's push that 0 up higher than we've used in previous examples. Okay, let's get started. We know we need to be looking at omega equals 1 and omega equals 10. We have our constant term. Now if we take our numerator, our j omega, from 1 we go to 10 and then up 20 dB. Play connect the dots. That's a straight line without corners. For our denominator, we're at 10, so we're flat until we get to 10. Now go forward one more decade. Because it's second order, we go down 40 dB. And again, connect the dots. Now we need to add all the pieces. Negative 26, negative 20, and 0. Negative 46. Slope of 0, slope of 0, slope of 20. From here, go forward one decade, go up 20 dB. Play connect the dots. And we will stop when we reach the next corner. Slope of 20, slope of minus 40, slope of 0, means slope of negative 20 dB per decade. Go forward one decade, go down 20 dB, put a dot, play connect the dots. There you go. That's what we're working with. That's the straight line approximation of this frequency response. I hope it's starting to make sense. Try to repeat these on your own, and then try some others on your own.